Hello, and welcome to our lecture for section 3.3 about the product and quotient rules. These are more of these nice shortcut rules that help us take derivatives of more and more complicated kinds of functions without having to do that horrifically messy limit of the difference quotient stuff every time. So for this first one, we've got a couple simple functions. The first one is a nice linear function, f of x, and then this happy little quadratic function over here. What I want you to do is find each of the derivatives of these two functions at x equals 3 for part A. And then for B, multiply the two functions together. You're going to have to FOIL this out to get the formula for this new function, the product of them, and then find the derivative of that function at x equals 3, and see is it the same thing as f prime of 3 times g prime of 3, your answer to A, which wasn't actually what A was asking, but we'll see if doing the derivative of a product is the same thing as just the product of the two derivatives. So let's try it out, see what you get, and pause it now because the answers will appear in 3, 2, 1. Welcome back. Here are the answers. So for the first one here, just getting the derivative of a linear function, the result is just the slope, and it doesn't matter whether you plug in x equals 3 or x is anything else. The slope of a linear function is constantly 2, so it's just 2. And then g prime of 3 is negative 24, which is what you get when you plug 3 into negative 8x plus 0, which is the derivative of this quadratic function, using just the power rule to do negative 4 times 2 to get that negative 8. Then for part B, f of x times g of x, I just FOILed it out. Here's what I got. Negative 8x cubed plus 12x plus 14x minus 21. I hope I didn't make any mistakes there. And then if you take the derivative of that using the power rule, you get negative 8 times 3 is negative 24 times x to the power 3 minus 1, which is 2, and then 12 times 2, which is 24, times x to the power 2 minus 1, and then the derivative of 14x is just 14, the derivative of 21 is 0, so you get that, and then I plugged in x equals 3 into that with my calculator here, and got a result of negative 130. So that sounds good, but is that the same thing as what we would have gotten if we did f prime of 3 times g prime of 3? Let's do that here. Well, f prime of 3 times g prime of 3 would be 2 is f prime of 3 times negative 24, which comes out to negative 48. So it looks like that's not the same thing. If we multiply the functions first and then get the derivative of that product, we got a totally different thing than just multiplying the product of the derivatives. So the answer to this is no. So in other words, the derivative with respect to x of a product of two other functions is not the same thing as just doing f prime times g prime. So what do we do instead? Well, we need this rule called the product rule, which looks like this. So it says that if you have these two differentiable functions, then the derivative of the product, this is like doing the derivative of that 24x cubed thing here, it's the same thing as just doing the derivative of f, that's f prime, times the original function g, plus the original f times the derivative of g, which we're sometimes going to use this Leibniz notation over here to write this. If we're just saying u is equal to f of x and v is equal to g of x, so these are like output variables we're using instead of y, then you get du over dx, that's the same thing as f prime of x, and then v is the same thing as g of x, and then the u is the same thing as the original f of x, and dv over dx means g prime of x. And we're using this u and v instead of y because it's confusing when you have different functions like y equals f of x, which is when we also say y is equal to g of x, if we're graphing them on the same thing, we can't really use y to stand for both of these things in these notations. And to prove why the product rule is true, we're actually still going, we can't just call it delta y anymore. We're going to call it delta f to stand for basically the same thing as delta y here. And likewise, delta g we'll just write as g of x plus h minus g of x. And we're gonna need this notation in this proof here that we'll see right now. But before we do that, let's also note that when we're using this notation where delta g is like the change in the output of the g function, this also implies that g of x plus h, like the new value of g, is equal to your g of x plus delta g. So the same thing as before when we were looking at linear functions. You take a starting y coordinate plus the change in the y coordinate. I hope those wind chimes aren't too annoying. But anyways, let's look at a proof of this here using the Leibniz notation to check that this works out. Or sorry, not actually using Leibniz notation at all. So starting with just the definition of the derivative of this function is what you get when you plug in x plus h minus the just f of x and times g of x minus what you get when you just plug in x with like any normal derivative divided by h, and then the limit as h approaches 0 of that. So to break this down, the problem is that this f of x plus h times g of x is kind of weird. So that's why I drew this nice rectangle here so we can see what are the different parts of this product. So if we think of multiplying g of x plus h times f of x plus h as just the area of a rectangle, just using regular old area equals length times width, where in this case the height or whatever is f of x plus h and the length, the other dimension, is g of x plus h. Well, f of x plus h is made up of the original f of x plus the change in f. Because remember, the delta f is the difference between the whole length of the side, f of x plus h, minus the f of x part. And same thing with this, like what I said before, g of x plus h, that total length there is equal to the sum of the starting length plus the change in g, the extra length. So when you find the area of this big rectangle or square sort of thing is made up of these four smaller parts. The blue part is the basic f of x times g of x, and then there's these two green parts that will be really important, because these green parts are actually what leads you to the terms that are left over in the end, as we'll see. So this one green part is the f of x function times the increase in g, and this lower green part is the width is the g of x times the height is the change in f, and that is given by those two parts there. And then there's this teeny weeny little orange part here, which has area, which is just the change in g times the change in f. And what we want to do is think about, to really understand why this works, we'll do the math first, but to really understand why it works, remember that we're taking the limit as all of this stuff approaches 0, as the change in g is going to get smaller and smaller as h gets smaller. So these green strips on the outer edge will get smaller and smaller. This green strip plus the orange strip plus this other green strip represent the change in the function. And one way you can see that is to see that this blue part here, you have f of x times g of x, that cancels out with this minus f of x times g of x, which is what you want to have happen, because you want the top of the difference quotient to always just be the change. So the change is represented by these other parts here. So what happens to the green and the orange parts as the change in x, also known as h, gets smaller and smaller? Well, I'm going to do the algebra rules here. I'm going to break this up into 3 fractions, all divided by h, because you could add them all up again. They have the same denominator to get h. So then when I break it up into 3 fractions, I'm going to take the limit of the 3 fractions separately to show that they all exist and to see what the whole limit, the original limit here, adds up to. So with this first one here, f of x is actually constant with respect to h, because h is the thing that's changing in this limit. So you can just take that f of x out of the limit using one of those limit laws. And then let's think about what happens to this. As the delta g gets smaller and smaller, that delta g is really the same thing as, remember, g of x plus h minus g of x here. And the limit of that change in the output divided by the corresponding change in the input, h, is the definition of this derivative here. So that's the definition of g prime. That's why this part of the limit, the limit of this vertical strip here, that area divided by h gets closer and closer to just f prime of x times g prime, sorry, f of x times g prime of x. And then the next term, the horizontal green part, the width is going to be that constant g of x, so I can take that g of x out of there, and then you have the limit of just the change in f divided by h, which is just the definition of the derivative of f prime. And then we have to do a weird trick with this one to see what happens here. This part, well, first I'm going to write it as delta f over h, because I want that to become f prime of x. So this part is going to get closer and closer to being f prime. The change in h divided by the change in g divided by the change in h gets closer and closer to being g prime of x. And why did I include this extra h? Well, I wanted to have these two derivatives, but then so I know what will happen to those, and then the h is going to approach 0. So in other words, this whole thing will add up, we'll get closer and closer to 0. And that was a trick you have to do to get both of those derivatives in 0 here to see what happens with this. So one way to think about why this works visually here is that as h approaches 0, we know that the whole area, everything is approaching 0. It's just that the orange square is going to approach 0 faster. It's got both of the side lengths are approaching 0, so it approaches 0 faster. But these other ones only have one side length that is approaching 0, and so when you divide by that change in x, the result just ends up being a nice derivative. So it works out nicely there. And okay, that is the proof of that. It's a pretty tricky to understand proof, but hopefully this gives you some intuitive idea for why you have to do it this way, instead of just taking the derivatives of the two functions separately and multiplying them. Okay, here is an example we can do. Try to use the product rule. Of course, this is your first time seeing it, so this might be really hard, but give it a shot. And if you get stuck, then you can see the answers. But first try it and pause it now, because the answers will appear in 3, 2, 1. And here are the answers. So I'll walk through how we did each of these steps, because this is the first time you're using it maybe. So first of all, with part A, our first function, which is like our f, is the x squared, and the second function, which is like the g, is the e to the x. So I'm going to write the derivative parts in orange and the original function parts in green here. So first, I did the derivative of the x squared part times the original e to the x function. That derivative of the x squared became 2x over here times the original e to the x. And then we have to add to that x squared times, that's the original function there, times the derivative of e to the x. And that derivative of e to the x is just e to the x. That's the rule from last time. Whoops. The derivative with respect to x of e to the x is equal to e to the x. So we're using that rule here. Anyways, over here, same idea. First, I'm taking the derivative of the first factor, 3x squared plus 5x, multiplied by the original second function, e to the power x. So the derivative of the 3x squared becomes 3 times 2 times x to the 1, which is 2 minus 1, plus 5 times 1. And then the second part here, we have the original 3x squared plus 5x unchanged, and then times the derivative of e to the x, which actually is also unchanged because it's equal to its own derivative. And this is what we get. So all of these end up having an e to the x. It's just that what's so you can combine like terms if you want, and leave the e to the x factored out. It doesn't really matter to me which way you write it. By the way, I'm happy with answers that look like this one or that look like this one. You can get an official check mark for that. But I like to simplify things just so I can check that everybody's getting the same answer. Okay, so then here is the last one here. The trick with this is to write the x squared part as x to the power -2, and then this is now a product. And then you can do the same thing with the product rules, and you can use the power rule with x to the -2. So the stuff works out the same way. Derivative of e to the x, doesn't change it, times the original second function, plus e to the x times the derivative of that x to the -2. That part over here becomes -2 times x to the -3. And then you end up with you have these two separate terms which both have e to the x, and then they both have x to a negative power in them, so you might want to combine it into one fraction, and you could write it like this, but you don't have to. Either one is really fine. Okay, let's look at the quotient rule. Okay, so the quotient rule is important. I don't want to show you the proof just yet. If you want to directly differentiate fractions like this, so like this last example here, we had to use the trick by turning it into x to the power -2 here. But what if that didn't work? Or what if you ended up with something that you weren't able to differentiate by putting it in that format? Then you might need this quotient rule. If using the product rule doesn't work like that last example. So the quotient rule says is if your function is the quotient of two functions, f of x divided by g of x, and they're each differentiable, then the derivative of the quotient is this big mess right here. G of x times f prime of x minus f of x times g prime of x divided by g of x squared. And I'll tell you how I first learned this and how I remember it. And my trick to memorizing it is this nursery rhyme, which is the way I've just always remembered it. You think of f as like the high part of the function. It's on top, so it's higher than g of x, and g is low. So I'm gonna make this rhyme by saying that the quotient rule is g of x is low, and then I'm gonna write the f prime of x as d high, because that's like the derivative of the high part, minus high times d low, that's the derivative of the g of x, divided by the square of what's below, which is still g. So let's say that out loud. Low d high minus high d low over the square of what's below. And that's the only way I've been able to remember this over the years. Okay, so let's prove it real quick. So we're going to say that saying Q is equal to F over G, that's equivalent to saying, well, if you just multiply both sides by G of X, that F is equal to G times Q. This is F of X is a very fashionable function because it's very GQ, you could say. And then, why do you want to do that? Because we can use the product rule, because G times Q is a product. So we're going to do the original G of X times the derivative of the second factor plus the derivative of the first factor G times the original second factor. And then that, first I'm just going to subtract this G prime of X times Q of X from both sides, because the goal here is to isolate this Q prime of X. We want to find a formula for Q prime of X. That's our goal. So subtract this other thing from both sides, then divide both sides by the G of X to cancel it out. So you just get Q prime of X by itself. And then, well, we also know that Q of X was defined to just be F of X over G of X in the first place. So I'm just going to make that substitution there. And then you can multiply both sides of this big fraction here by G of X. And you have to distribute it into the two terms. Over here, it will cancel out. And on the left term, you get G of X times F prime of X. And I also need to multiply that on the bottom of the fraction so that I don't actually change it. And that's how you get this last step here, that the derivative of Q is low d high minus high d low over the square of what's below. Now let's try to use it with this example. Again, these are tricky, but try your best, and pause it now to try it, because the answers will appear in 3, 2, 1, and here they are. So the first one here, so what I tried to do here with the colors is keep all of the denominators orange so that you can help keep track of it that way. And I kept the numerators green. So here you have low d high minus high d low over the square of what's below. The derivative of 5x squared becomes 10x. The derivative of x cubed is 3x squared. The derivative of 1 is 0, so that just becomes 3x squared there. And then I multiplied everything out, and I factored it just to see if there was anything I could simplify. I don't think there's anything here to simplify, but it doesn't hurt to factor it. Either way, both of those answers are correct. With the second one, same idea. I have the bottom in orange, so I have low d high minus high d low over the square of what's below. And with this one, the derivative of 1 is 0, and that means this whole thing is going to become 0. It's 1 plus e to the x times 0. And you end up with minus 1 times the derivative of 1 is 0, plus the derivative of e to the x is still e to the x. So we just have this negative 1 times e to the x divided by the denominator squared. Same thing here. I have x squared times, so low d high minus high d low. The derivative of x squared becomes negative 2x over x squared squared becomes x to the fourth. And then I just reduce a factor of x from the top and bottom and factor out the e to the x, and you've got this result. And this, let's just check that this is the same as the result that we got using the product rule before up here. We had e to the x. Yeah, so here I wrote it as x to the negative 2, used the product rule. We got the same thing, e to the x times x minus 2 all over x cubed. And that's another reason why you might want to practice simplifying things, because sometimes different people will get different answers using different methods that are really equivalent expressions, but it's hard to tell unless you simplify it as much as possible. So simplifying these made it so I could really tell they were the same thing. So that's enough of that. And again, I want to emphasize that using more than one rule to do the same thing is always a good habit. It's more than twice as good as just doing it once. So let's practice that. We're going to find the derivative of t to the power 5 3 different ways. One, just using the power rule. I'll give you the answer to that right away. Hopefully you can do this. You'll get 5t to the power 4. Okay, so I already did part A for you. Then for part B, find the derivative of the same function, but write it as t squared times t to the power 3. That's the same as t to the 5th, and you should be able to differentiate it like a product that way. And then also find the same derivative using the quotient rule. Make sure you get the same answer for A, B, and C, because these are all 3 different ways of computing the same derivative. And it will be more than 3 times as good as just doing it once. Then let's do this to use the, what am I trying to say? Let's do this derivative. We already did this one before, but we're gonna do it a weird way using the quotient rule by writing it as that x squared, write it as 1 over x to the negative 2. And then for part 3, we're going to find this derivative using the product rule, and hopefully it comes out as the same derivative we found before in the beginning with the warm-up, not using the product rule. Here are those solutions. So for P1 part B, oops, we can't quite see it here. Here are the steps I did using the product rule. I wrote the stuff that came from the t cubed in orange here. So its derivative is 3t squared. And here you do the derivative of t squared is 2t. Both of them come out to be t to the 4th power, and it adds up to 5t to the 4th like it should. So that sounds good. And then here's the steps I did with the quotient rule. I have low, d high, minus high, d low over the square of what's below. Stuff cancels out and you end up with 5t to the 4th. So that's good. And then for problem number 2 here, this one is a little bit tricky, but the derivative of x to the negative 2 becomes negative 2x to the negative 3 here, and the rest of the stuff in the quotient rule is laid out like so. But then this might look different from the answer to this question before, but what you can do is in this step, if you have this x to the negative 4th here, just write both sides times x to the 4th in the top times x to the 4th, and that just cancels out that x to the 4th in the bottom. And then you just distribute that x to the 4th into these terms in the top, and this is what we end up with, which I believe is the same as that same problem before, which we did with a product rule, which is the more straightforward way here. So it's easier with the product rule, but the quotient rule works as well. Then, with practice problem 3 here, all I did was I wrote the 2x minus 3. I wrote the stuff from that in green and the stuff from negative 4x squared plus 7 in orange. So the derivative of the orange part becomes just negative 8x plus 0. The derivative of the green part is just 2. Foil everything out. combine like terms, and we get the same answer as we had from that original warm-up. So yeah, it looks like the product rule works, and we get, where did the result go? Right here. Yeah, whoops. That is the same result we got before, so it looks like the product rule works, and it agrees with the quotient rule, and it agrees with doing things oh, we're not there yet. Whoops. The old-fashioned way, just using the power rule like this. So all these rules seem to agree with each other, so that's good. So we can keep using them confidently. It looks like they do derivatives properly, and I'll see you in class on Tuesday afternoon.